All right, thank you very much. So this is some research I did with 3 students at Willamette University who have since all graduated, and David is selecting a graduate school as we speak. So it all started with this problem a little while ago with its argument between Newton and Gregory about how many, so you have a sphere in the middle, you have a bunch of spheres that all come in contact with it, and the question is how many can you pack in? Newton thought it was 12, Gregory thought it was 13. What Gregory failed to realize is that 322 years later, I would be mentioning this problem in a Gathering for Gardner 12. So, of course, the answer is 12. But it's actually pretty tricky to prove, and there was arguments. And it wasn't until the 1950s that we had a proof. And that, I think there's even some debate about who proved it first. So this is the idea of this Newton number, or kissing number. The spheres kiss each other. They just touch. The Newton number of the sphere is 12. And also in the 50s, Hodwiger proposed this variation. So for the spheres, it doesn't matter. But for the rectangles, you can decide whether they're allowed to rotate or not. And for the Newton number, they are, and for the Hodwiger number, they're not. So you can see for a rectangle, however skinny the rectangle is, the Hodwiger number is always 8. You can always fit 8 rectangles around that central one. But the skinnier the rectangle, the larger the Newton number. You can fit more of those things in the top and bottom. So I'm going to share with you the variation that we came up with that we call the star number. And it's sort of based off the Hodwiger number with these 2 differences. The first is that these red shapes around the outside are allowed to overlap, not just touch the central shape, but not even touch each other. So the idea is intersection. So the red shapes intersect the middle one, but not each other. And so you can see for this particular example, the 2x1 rectangle, the Newton number for this rectangle is 10, the Hodwiger number is 8, and the star number is 4. I can fit at most 4 of those red rectangles intersecting the corners. So they are all different in general. So I'll show you a few cool examples that I particularly like. For a d-dimensional cube, the Hodwiger number in general is 3 to the d minus 1. So you can see this Rubik's Cube in 3 dimensions. You can fit up to 26 little cubes, all intersecting the central one. But the star number is just 2 to the d, so you can only fit 8. So this is an example for which the Hodwiger number is much larger, or as large as you want, bigger than the star number. But going the other way, the L shape, the Hodwiger number of the L shape is always exactly 7, regardless of how skinny the L is. But the star number is bigger and bigger for skinnier L's. In particular, if it's a polyomino made out of n squares, the star number is exactly n plus 2. And there's this really cool theorem by Grunbaum in 1961 about the Hodwiger number of a convex polygon. So the Hodwiger number of every convex polygon is 6 unless the polygon is a parallelogram, and then it's 8. And we proved that the star number of every convex polygon is 5 unless it's a parallelogram, and then it's 4. So it's really neat to me, both that the parallelogram is the special case for both of these theorems. You can see this parallelogram, it's the same idea as the rectangle, where you can just shear it and get any parallelogram that way too. The parallelogram is a special case for both of them. But for the Hodwiger number, for a non-parallelogram, the number goes down, and for the star number for a non-parallelogram, the number goes up. And that was really cool to me. So here's some questions we still have. This picture is supposed to indicate the Newton number for the L shape is also unbounded. So as you get skinnier L's, the Newton number still gets larger and larger. I'd love to find some type of shape whose Newton number is fixed or bounded, and the star number grows. And also for polyomino with n squares, we think the L shape has largest star number, but we don't know for sure. So I'd love to answer those questions. And I also just want to give a quick mention that I will be, again, co-organizing the MOVES conference, the Mathematics of Various Entertaining Subjects, next August 2017, the 6th through the 8th. So I hope I see you all there. Thank you very much.